Hi everybody. Today we'll see how acids and bases behave in water and what happens when you mix the two together. Now on this flip I wrote weak acid and strong acid. Amongst weak acids, the differences between them are that only some of the weak acid dissociates, while all of the strong acids you put in water dissociate. For example, hydrofluoric acid would go in equilibrium with a proton and fluoride anion. Now I can also go in the reverse direction. That's so special about weak acids. For strong acids, let's say nitric acid, they can't go back. Or they fully dissociate and never go back. So let's try calculating the pH of weak acids, bases, and so on. The pH is just the negative log of the concentration of protons. In other words, more protons means lower the pH. Here, let's calculate the pH of acetic acid. So our reaction R is, let me get some more space. So our reaction R is CH3COOH going back and forth into acetate, CH3COO minus, and hydrogen protons. I, the initial concentrations, let's make acetic acid 1 molar. We have 0 on both sides. The change, C, is minus X and plus X for both ions. E, equilibrium, is 1x more for acetic acid and simply x more for both ions. Now our Ka, which is these numbers, will be equal to the ion concentration squared, or the product squared, divided by the reactant concentrations. Now that would mean that x squared divided by 1 minus x equals 1.8 times 10 to the negative fifth. But this minus x is what makes it a lot harder. A simple trick is only a tiny part of it dissociates, so we're just going to drop the x. So therefore x squared equals 1.8 times 10 to the negative fifth, which says that x is 0.0042, and after a few taps in the calculator, you'll find the pH value equal to 2.372. Well, vinegar is 2.5. So vinegar is a close to 1 mole solution of acetic acid. Now, you can always interpret it for HF and CH3OH anytime you want. But right now, let's go on to strong acids. Strong acids, as I said, fully dissociate. So Ka is just 1 for all of these. For example, R would be HCl, just going to H plus and Cl minus. Now I is 1 molar and 0 for both ions. C would be minus X, plus X, and also plus X. E equals 1 minus X more and X for both of them. If we just interpret it all in, we're going to get this equals 1. Now, because we got rid of this minus X, X is going to become X squared equals 1, and X equals 1. Now take the negative log, if there's no number, it's going to be 10, of 1. Then it's going to become 0. So 1 more HCl has a pH of 0. Well, because there's 1 more hydrogen ions. Now, on the pH scale, you're usually going to find 0 to 14. If it's a 0, it's 1 more. The 14 is 10 to the negative 14th power molar. Now, let's move on to the bases. Now, bases right here are lying here. Now, the KEQ for base is not Ka, it's a KB. Now let's find the pH of NH3 or ammonia. So we have R, the reaction, NH3. Now it's a base, so it's going to accept a proton. Going in equilibrium, becoming ammonium plus hydroxide. I is 1 molar, 0, 0. We never put water in our equations. C is minus X and plus X for both sides. E is 1 minus X M and an X more for both ions. Now more is simply moles per liter. So let's just do the same thing we did for our equation and for our last one. Now things are going to look simple here. Just do what we did the whole time with acetic acid. Except you're going to have to do one more extra step this time. Now once you put in the negative log of x, which is 0.0042, you're going to get 2.372. But because it's a pKb, you're actually going to get the POH. But the good thing about it is we can easily solve for the pH. Because POH plus pH always equals 14 at room temperature. So we can do 14 minus 2.372, which makes 11.628. So ammonia, 1 mole of ammonia is 11.628 on the pH scale. Now, let's see the strong base. Like strong acids, the Kb of a strong base is always 1. It fully dissociates into KOH plus H2O, means that it's going to become K plus H2O plus OH minus. So this is our reaction. I is 1 more in for potassium hydroxide, 1 more. For here it's going to be 0 for now, and then C is going to be minus X for potassium hydroxide, plus X for both ions, and then E would be 1 minus X more for potassium hydroxide, X for just potassium cation, and X for the hydroxide anion. So we're going to interpret the numbers, and we're always going to get a pH of 14, because we're going to end up with the POH of 0. So let's start interpreting the numbers. 1 minus x squared divided by 1 minus x equals the Kb 1. X squared is going to equal 1 because we always want to cancel out the minus x. Because 1 square root is always 1, we're going to get x equals 1. And then we're going to interpret this x into negative log, which is 0. Now 0 plus the pH equals 14. Subtract 0 for both sides. And then we're going to get the pH equal 14. Let's try mixing acids and bases. First, let's try strong acid plus strong base. So HCl plus NaOH. Well, you're obviously going to see this because the HCl dissociates and NaOH accepts a proton, but then we're going to have extra H2 on this side. We always get H plus and OH together and get H2O. And these two are just table salt, NaCl. So these guys are going to react to form H2O plus NaCl, or salt water. Now back in the weak acid to weak base, I made this sign. This sign means equilibrium, or the reaction can go forward, like all reactions, but it can also go backward. For example, our weak acid reaction, I mentioned earlier. In water, hydrogen fluoride becomes its ions, and it can also come back to hydrogen fluoride. But there are some reactions that are not equilibrium. For example, the strong acid hydrogen chloride story, it's not going back. Its conjugate base is too weak to actually grab a proton. But also, there are always factors that affect equilibrium. We're going to talk about that in a later video. Thanks for watching. Bye!